Okay, so today we're going to continue our discussion of the Coriolis force. We've been talking about it in the context of it balancing the wind stress in the Ekman transport, or the frictional force, turbulent vertical mixing. Today we're going to talk about it being in balance with the pressure gradient force. We're going to see that the funny force diagram, where we have flow going in a different direction than the forces being applied, still persists in this case. We're just going to adapt the old diagram to a new purpose. But we're also going to begin to think about how the geostrophic balance represents the motion below this wind-driven Ekman layer. And that's going to be a really important concept, probably the most important, maybe the most important concept in all of geophysical fluid dynamics. So we're going to pick up with our usual review of non-dimensionalization and the balances that we've talked about. Then we're going to make this analogy between the geostrophic balance and the Ekman balance, and that's going to be using that same force diagram. Then we're going to go through a couple of specific cases: the constant density case, the barotropic case, the baroclinic geostrophic balances. Those are each all talking about different versions of the pressure gradient force. And then we're also going to touch on this concept of superposition and linearity, which is going to be really useful to back up the schematic we've been drawing with those deep flows, and then adding the Ekman shear on top. We're going to see what assumptions justify that decomposition. Okay, non-dimensionalization. So the way that we've been talking about doing this is you estimate the size of the dimensions: time, length, velocity, depth, etc. You scale all the terms and equations by these. It's pretty much just writing down which one goes with which. Sometimes there's some decision to be made because you might have a difference or a total or something like that you have to worry about. But anyway, once you have written down all of the scales for all the terms in the equation, you collect them all together into non-dimensional quantities. We've seen the Ekman number, we've seen the Reynolds number, we've seen the Rossby number. Those dimensionless ratios are the ways that different physical situations distinguish themselves in a way that's independent of the units that you're using, of the size of the planet, the rotation rate of the planet, whatever. That's fundamental GFD kind of thinking. Okay, so some of the ones that we've talked about are the Reynolds number, the Rossby number, the temporal Rossby number, and the Ekman number. And in each of these cases, we can think of these either as a ratio of, say, the velocity times length over viscosity for the Reynolds number, or the velocity over the Coriolis, local Coriolis parameter times length for Rossby number. Or we can think of it as the ratio between two terms in the equations: the momentum advection versus the viscous dissipation terms in the horizontal momentum equations, or it could be the vertical momentum equations as well for the Reynolds number. The momentum advection over the Coriolis parameter and the horizontal momentum equation. The momentum tendency, that is ddt of the momentum over the Coriolis parameter in the temporal Rossby number case, or the viscous dissipation or the turbulent mixing term versus the Coriolis parameter for the Ekman number. And so here's an example. When we go to the full momentum equation, the dv dt term scales like a velocity over a time scale. The v dot grad v term scales like a velocity squared, one velocity, two velocities, over length, because the grad here is a spatial derivative. F cross v scales like Coriolis parameter times the velocity. This one is a little complicated, but there's some kind of pressure scaling, there's some kind of length, there's some kind of density. A little bit confusing. The gravity term scales like itself, gravity. And then the viscous term scales like the viscosity times the velocity. And we could take it either as the horizontal viscosity or the vertical. This one's written with the H's, so the vertical direction. So, and often that one is the more important version. If I divide through this equation, each of these scales by this term, setting the Coriolis parameter term to be order 1, saying that one's always important, what could it balance with? Then I find that this term divided by this is the Rossby number. This term divided by this is the temporal Rossby number. this term divided by itself is the Coriolis parameter. We don't know about this. We don't know about this. Let's not worry about those for now. But this term over here is the Ekman number. So rather than just introducing those separately, you can think of it as just deciding which terms in the equation are the big ones. So when we go to the Taylor-Proudman theorem, there's a certain set of these dimensionless numbers that are small, like this. And so Rossby, Ekman are all small, make these terms in white negligible in comparison to the terms in red. The inertial oscillations has an order 1 temporal Rossby number, a small advective Rossby number, and a small Ekman number. The Ekman layer, balance between the Coriolis force and the friction, has an order 1 Ekman number, a small Rossby, both flavors. The hydrostatic balance is a little bit different than these because it's in the vertical direction momentum equation, so we don't have the Rossby numbers and things, which are focused on the horizontal, because we're normally neglecting the contribution of the Coriolis force in the vertical direction. But anyway, we have a balance between these two terms, vertical pressure gradient and gravity. And inertial oscillations has appeared for a second time for a reason that I don't understand. Sorry, some repeated slides here. Okay. Okay. So here's where we settled on the jumping back to the force diagram physical balance. So we take a small Rossby number, advective and temporal. We take an order 1 Ekman number, and that gives us a balance of forces between the friction force and the Coriolis force. This is sort of the physical understanding of what's behind the Ekman transport. And we said you can think about that as being the wind, which orients the friction force this way, balancing the Coriolis force in the opposite direction. In order to get the Coriolis force on average, you have to have a depth integrated transport 90 degrees to the left of the wind, of the Coriolis force, which is 90 degrees to the right of the wind. So this is our basic force balance. And we thought of this as a deviation, a sheared layer that is in the upper ocean driven by the wind. It's not like Taylor-Proudman because it has vertical shear in the direction of F, but it didn't have to be like Taylor-Proudman because Taylor-Proudman, we neglected the friction force. So when we have violated the conditions of Taylor-Proudman, when we are in this near surface layer where the Ekman number is order 1, and therefore we are allowed to have shear in the direction of the rotation axis. And when we think about how it works, it goes like this. And we talked about this as being a deviation from a deep mean velocity in a surface layer. So U minus U bar, V minus V bar up here in the Ekman flow. We also talked about the Ekman spiral, but remember the Ekman spiral is not terribly robust in the face of changes in the vertical or in time or in space of the viscosity or turbulence. Whereas the Ekman transport, this one is pretty robust, even in the face of those changes. Okay. You might have gotten confused with this diagram, figuring out what direction V goes in. We had this homework problem where it was actually pretty hard to think about how that goes. So I wanted to do a little bit of vector manipulation to write this as not as an expression for the Coriolis force balances the friction force, but actually what is, let's solve for this velocity, including the cross product, and see how that looks. That goes a little bit like this. If we take the so-called back cab rule, B A dot C, C A dot B is the triple product of A cross B cross C. This is an identity. If you don't trust this, you can go through all the components one by one. But this is always true in 3 dimensions anyway, that it looks like this. So here we have F cross VE, and that doesn't look like any of these terms, but maybe it looks a little bit like B cross C. So if we take F cross VE, that looks a lot like A cross B cross C. So we can use the back cab rule in that case. So F cross VE is F dot VE minus VE F dot F, which is just the magnitude of F squared, which equals F cross F. So this is taking this F cross here, apply it to this F on the right-hand side, which is F cross F. simplify, because now we can actually solve this side of the equation for VE. Then we get F cross F. Oh, we missed one step. F is in the vertical direction, VE is in the horizontal direction, so F dot VE is 0. Cross that term off the list. Now we just have VE F squared equals F cross F. So VE equals, and there's a minus sign there, so move the minus sign over, minus F cross F over F squared. Or, to make it simpler, we can cancel one of the F's in the upstairs, which is a vector F, with one of the F's in the downstairs, which is a magnitude of F. And in order to do that, we get a Z hat in the upstairs, decreasing the F by a power, and the downstairs. And I have reversed the order of the Z hat was in the first, and there was a minus sign, but if we put that second, then we can remove the minus sign. So F cross Z hat over F equals the Ekman velocity. This is a lot simpler formula than one we were using before, because now it just tells you what direction the Ekman flow is in. Friction force across Z over F. Works just fine unless F is 0. Okay. All right. So what's geostrophy then? This is the topic of the day. Geostrophy is different from the Ekman force in that we have neglected this Ekman number. Now we're going to say this is small too. So Rossby number is small, temporal Rossby number is small, and the Ekman number is small, but the pressure gradient is not necessarily small. We said the pressure gradient was one that we didn't even know how to scale it way back when we were looking at these. So how big is that term? Don't know. Indeterminate. But what if it's big enough that it balances with this term? And we're actually going to see that the gravity term comes into this as well, but in a different direction. So these three terms together are the ones we're thinking about now. Okay. So let's just say F cross V. This is the horizontal momentum equation. F cross V equals minus gradient of pressure over density. Fine. That's something. It looks an awful lot like the F cross V minus the friction force version we had before. So we can just use the same force diagram, except now we have the pressure gradient force, which is coming from this term. And so the high pressure is here and the low pressure is there. So the force pushes from high pressure to low pressure. If we want to balance that against this term, the Coriolis force needs to point in the opposite direction, okay? Which means that the geostrophic flow, the flow that is balancing the pressure gradient force through the Coriolis effect, is 90 degrees to the left of the Coriolis force, which in order for this to balance this, it means that it is 90 degrees to the right of the pressure gradient force. Okay, that's cool. This deeper flow that we've been kind of waving our hands about, what's different about this flow from this Ekman layer flow? Well, the Rossby number of it is small because the Rossby number didn't vary that much in the vertical. The temporal Rossby number is small because the time scale doesn't vary very much in the vertical. But what does vary in the vertical is when we get outside, when H gets big, that is when the depth of the layer we're considering gets taller and taller and taller, eventually H gets so big that the Ekman number becomes small. So then this is small, this is small, this is small. So outside of the Ekman layer, the geostrophic flow is the next thing that takes over. And actually there probably was some geostrophic flow within the Ekman layer as well. It just doesn't have any shear in it. So the Ekman layer was the part that was just giving this shear within that layer, whereas the geostrophic flow is relatively uniform in the vertical. We're going to talk in a minute about how it deviates from uniform in the vertical, but I want you to have the initial impression that geostrophic flow tends to be uniform in the vertical. That's a good starting point. Okay, so the geostrophic flow is perpendicular to the pressure gradient force. That means that it is along the isobars. So high pressure would go along this way, low pressure goes along this way, and the flow is right along the high pressure lines. We're going to see more examples of that. So geostrophic flow is perpendicular to the pressure gradient, thus it's along the isobar. So I should say isobar is a line of constant pressure. So high pressure to high pressure to high pressure to high pressure is an isobar. Iso meaning same, bar meaning pressure. Okay, we can play the same game with the triple products. Bloop, 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 bloop. Back cab rule, except now we're playing it on this balance, which is the same as this one up here, except now I put a subscript G to imply the geostrophic velocity. Geostrophic velocity, the Coriolis force on it, is balanced with the pressure gradient force. So, take F cross this equation, F cross blah, blah, blah. Once again, the geostrophic velocity is in the horizontal direction, so F dot geostrophic velocity is 0. But this term survives, Vg F squared. Over here we've got the F cross grad P over rho. There we go. Here's the geostrophic velocity written like this. In this case, if the minus sign was already there, we don't switch the order. We can keep the z hat first. It comes from F, the vector, divided by F, the magnitude. So z hat cross grad P over F rho. That's the geostrophic velocity. Geostrophic velocity, Ekman velocity. F cross z hat over F. Friction cross z hat over F. Geostrophic velocity, z hat cross gradient of pressure over F rho. Great. You may be thinking, okay, well, there are these pressures everywhere, but where is the pressure coming from? What is the pressure? That's crazy. You would be right to think that, because figuring out where the pressure comes from is the whole essence of the geostrophic velocity and why it's confusing. Because you don't know which is the cart and which is the horse. There's pressure there because there's flow, and that flow is apparently setting up a pressure field. There's flow there because there's pressure, and that flow is there because there's a pressure field. Who gets started? How does that whole system work? Who initiates what? We're going to come to that. But for now, let's just think back to our hydrostatic pressure relation, which gives us a good handle on the pressure. Notice that this is the vertical direction crossed into the full 3D pressure gradient, which means that this is really the horizontal pressure gradient that's important in this equation, because any vertical component of pressure here would be canceled by this z hat. Okay, this is the horizontal pressure gradient that matters for the geostrophic flow. But we have to go to the vertical pressure equation to find out about the horizontal pressure variations. The hydrostatic balance neglects this acceleration in the vertical term. Get me a z dependence of the pressure term. We talked about this in the atmosphere, with it being exponential. We talked about it in a constant density or nearly constant density Busenesque ocean, being approximately linear with depth. It's all coming from this equation, dp dz equals minus rho g. But we might integrate both sides of this equation. So p, that's the integral of dp dz, equals the integral of z to whatever z we're going to from some reference value of z. There's a minus sign. I can get rid of the minus sign by flipping those two. So from a reference value of z down to z, rho g. We talked about this as being the weight above you per unit area, because this is the weight above you per unit volume integrated in the vertical, so it's the weight above you per unit area. Okay, we have the hydrostatic balance. That's got this in the vertical momentum equation. But still, this doesn't help us figure out what makes there be weight above you, or anomalous weight above you, even more precisely, because we don't care about the pressure itself. We care about the horizontal changes in pressure. That's what's driving the geostrophic velocity. So we'll jump back to our pillows and bricks example and think about it from the pillows and bricks perspective. Here we have a stack of pillows representing light water, taller stack of pillows, thicker layer of light water, small stack of pillows, thinner layer of light water, and then bricks underneath representing the variations in the picnic line. In this surface layer, we have more weight of pillows above you because this pile of pillows goes higher than this pile of pillows or this pile of pillows. So the high pressure is under this pile of pillows. The lower, relatively lower pressure at this horizontal level is like that. So high pressure, low pressure, low pressure. We expect to have a geostrophic velocity because there is a high pressure anomaly here in the middle of this, underneath this sea surface height. If we go down here below the picnic line, it's not so obvious because, yes, there was a low pressure anomaly here, but now the bricks start higher up on these two than they do here. So we're accumulating weight faster once we're below the picnic line in these locations than we are here. And so we might have a reduced horizontal pressure gradient down here below the picnic line. We talked about this a little bit in the sense of the Ekman under cyclonic and anticyclonic winds driving this upwelling and downwelling. So this is the kind of process an upwelling can lead to an anomaly in both the surface height, therefore making in this surface layer, making a low pressure here underneath the surface divergence, high pressure here to the sides. But then when we go down below the picnic line, we have this anomaly in bricks coming up to the surface versus the bricks starting deeper down over here. Similarly, if we had the opposite, an anticyclonic wind, we might have a surface convergence, which leads to a sea surface high, a picnic line exceptionally deep, and so we would have high pressure anomaly in the middle, and we would have low pressure on the sides over here, and then maybe less of a gradient below the picnic line. So we're going to start thinking about having ocean surface anomalies, sea surface height anomalies versus the geoid, giving us pressure anomalies. In a constant density ocean, this is a pretty easy thing to do because we don't have to worry about that compensation of the picnic line going down or whatever. We just start counting the pressure as a function of height based on some constant density. If the density is constant and g is constant, I can do this integral pretty easily. I can do it anywhere. The only question is where you start at the top. What's your reference level, that z naught? If you put that z naught at the surface of the ocean and assume that the atmospheric pressure variations are negligible, so this is at the same pressure, same pressure, same pressure, same pressure, same pressure, this is the solution to this differential equation for constant density. It says the pressure goes like rho naught g z minus z, so it accumulates linearly in the vertical direction. The deeper you go, the more pressure you have. But there's no horizontal variation in that rho naught g z part. There is a horizontal variation in where the reference level is. Do you start high up, where you're under a sea surface height? Or do you start low down, where you're under a sea surface low? That gives you a lateral variation, a variation in x and y, of the sea surface height, this anomaly, this eta. So the pressure is a function of x and y and z, but in very different ways. It's a function of z in a trivial way, in this constant density ocean, but it's a pressure function of x and y due to these anomalies in surface height from place to place. So if we go to a constant density version of this force diagram, we can replace everywhere where there's high pressure with sea surface height. Everywhere where there's low pressure with sea surface low. We get a geostrophic flow that goes like this, and if you work out all the factors, the geostrophic velocity goes like z hat cross g times gradient of eta, gradient of the sea surface height, over f. So this tells us that geostrophic velocity in a constant density ocean flows in a direction perpendicular to the gradients of sea surface height, which means that it flows along the isolines of sea surface height. If you mapped the sea surface height contours, it would be flowing around and around on those sea surface contours. It also varies with f in a funny kind of inverse way, which means that this response is different at different latitudes. Now, you might be wondering, did we violate anything to do with the Taylor-Proudman assumption in this? In fact, we didn't. We have constant density, we have negligible friction, we have low Rossby number, both advective and temporal, so we have all of the conditions for the Taylor-Proudman theorem to apply. The Taylor-Proudman theorem does apply. In fact, this geostrophic velocity is independent of height. It's the same at every depth. It just depends on the surface, sea surface height variations from place to place. But it doesn't depend on depth. The pressure field depended on depth, but only in this trivial way that it linearly accumulated with the same rate of accumulation everywhere. So the pressure does depend on depth, but the horizontal gradient of pressure does not depend on depth. It only depends on the sea surface height in the special case of constant density fluid. So for constant density fluid, the geostrophic flow is actually in Taylor columns. They don't tilt over, they just move around like this. No shear from top to bottom in the geostrophic flow. And here's the little bit of algebra that shows that. But that's the situation. So when we go back to the lab tank experiment, which is a relatively constant density fluid, you can think, what's going on here? Well, we see the inertial oscillations on the very high frequency flow, and that had to do with the Rossby number being slightly non-negligibly small, that there was some Rossby number, you see the inertial oscillations. But now, this flow that's carrying around these curtains, or Taylor columns, is almost surely a geostrophic flow. There is a sea surface height anomaly from the parabolic surface that a rotating tank would have that would be with no motion. It's there because of that stirring in the beginning. And that sea surface height anomaly, see these big circles? Those all are high and low pressure anomalies that are transporting the fluid around. They're the inertial oscillations. Now, if we had put dye down in the bottom boundary layer where there's a friction effect, you would have actually seen that there was transport across these layers because there is a bottom Ekman layer here. But outside of that bottom Ekman layer in the interior of the fluid where this dye was injected, there is a constant density geostrophic flow at play in this situation, or nearly geostrophic flow. So these motions are associated with a sea surface height anomaly, tank height anomaly, whatever you want to think of it, and you can actually see that this one is a big old anticyclone, this one is a big old cyclone, etc. Okay, so we're going to get to that in a second. Okay, we can actually generalize away from constant density one step by considering what's called a barotropic ocean, which is a little bit more general than a constant density ocean. That says that, okay, the density can vary, but it only varies in such a way that the density varies on pressure surfaces. It doesn't vary with X and Y independently, it doesn't vary with salinity or temperature independently, it doesn't vary with whatever, Coriolis parameter, whatever. It just varies as a function of pressure. This is a useful one because this is a lot of what you would think the compressibility effect would be. So, we talked about the variations of density in the equation of state being because of salinity, temperature, and pressure. So if we neglect the variations to do with salinity and temperature, then there's still a variation to do with pressure, the compressibility part. A barotropic ocean includes that part, but it doesn't include the part that has to do with variations of salinity and temperature that would change the density. But, okay, so now we have a constant salinity, constant potential temperature ocean. Actually, it could be temperature, not only potential temperature, because this actually includes the compressibility effect. All right, that was subtle, but you can listen to that a couple times and think about it hard if you want. In this case, we can't solve this equation outright in a closed form. We have to write that the pressure is an integral from that spatially varying sea surface height down to some z level of this now spatially varying rho g dz. But we can still go through the game of writing out the pressure gradient for us, thinking about this, and we actually can just substitute for the pressure in that system and find that this is the horizontal gradient of this object right here. That's a complicated thing. It varies in x and y because of the sea surface height. It also varies in x and y because of the density field. But the point is, this whole object is similar enough that we can still think of it as being variations like this, where the high pressure, high sea surface anomaly is driving the horizontal gradient of this motion. There's also a piece of it that's coming where the horizontal gradient hits the pressure, hits the density, which then depends on the pressure, but it does it in such a way that we still don't get du dz, any shear in this velocity field. We just get a slightly different version of what the geostrophic velocity is, but it's still not sheared in the vertical. It's just moving around in these Taylor columns, and it tends to have most of the dependence still come from the horizontal variations of the sea surface height rather than the horizontal variations of the density. Here's a little math which goes through the process of showing you that it's still Taylor-Proudman, and the key question is whether this term vanishes. And since this is a curl, this is the gradient of density crossed into the gradient of pressure, but if density is a function of pressure, then this is effectively a derivative of whatever that function is times gradient of pressure cross gradient of pressure, which is 0. So, bing, 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 that gives you, this is still a Taylor-Proudman theorem-like flow, even though it isn't quite as simple as being the G grad eta form that we had before, because there's this complicated correction factor top and bottom. Okay? So, barotropic hydrostatic geostrophic flow is in Taylor columns along the isobars, the same way that constant density hydrostatic geostrophic flow was in Taylor columns along isobars. Okay, so let's think a little bit about the practicalities of this. What happens if we have a high sea surface height? Well, the pressure gradient force is pushing outward from the high. We need a Coriolis force that's pushing inward to balance it, which means that we need a flow going around and around in this direction. So we get a flow that, at least in the northern hemisphere, would be clockwise around high pressure. And then in this case, with a low pressure, now the pressure gradient force is pointing inward all the way around, which means that we need a flow in the opposite direction to balance it with the Coriolis force. That gives us counterclockwise flow around a low pressure system in the northern hemisphere. In both hemispheres, we have an anticyclone that is anti-rotation in the direction of the Earth around a high pressure system, and a low leads to a cyclone, which is a rotation in the same direction as the Earth in around a low system. So low systems are cyclones, same direction, cyclonic, same direction as the rotation of the Earth. You can think about it with the right hand rule with your thumb pointing up. That's the direction of F. F is positive, so it goes around like this, which is counterclockwise. So this is cyclonic. This is anticyclonic, thumb down, rotating around like this. Anticyclone around a high pressure, cyclone around a low pressure. In the northern hemisphere, this is clockwise, this is counterclockwise. Now we go to the southern hemisphere. Anticyclone is still around a high pressure zone, but it's going the other way because now F is pointing, from into the surface. The whole Earth is going around like this. We're pointing F upwards towards the North Pole, which means that it's down into the surface. So flip it upside down, put upside down, right side up, down under, and we get a high pressure system with F being negative is going not in the direction your fingers curl, but the opposite direction. So an anticyclone is counterclockwise, still around a high pressure system. Low is now a cyclone, but a cyclone goes the other way. It goes clockwise in the southern hemisphere. And this is kind of the 3D visualization of what's going on from Collings, where there's the horizontal pressure gradient force in balance with the Coriolis force, which means that the geostrophic current is going like this. And if you look up to the surface, here's the rotating around and around the elevated sea surface height anomaly in the middle. Okay. Changing gears a little bit, let's jump back, review our balances again. So we have a full momentum equation. We can non-dimensionalize this by scaling each of the terms and thinking about the relative sizes. inertial oscillations is when the effective Rossby number is small, but the temporal Rossby number is order 1. The Ekman number is small, so friction is negligible. The two yellow terms are the remaining ones. Ekman layer. Ekman number is order 1. Both Rossby numbers are small. Blue terms are the key ones for leading to the shear within the Ekman layer, which is the Ekman transport when vertically integrated. The hydrostatic balance is the pressure gradient is balanced against gravity in the vertical direction, and it has to do with the aspect ratio. But only the direction of gravity is constrained by this. So we don't know much about the horizontal pressure gradient from this unless we do this kind of spatial thinking about the variations in sea surface height. The geostrophic balance, new one for us, is the balance between the Coriolis force and the pressure gradient force. Now we're talking about the horizontal pressure gradient force, not the vertical pressure gradient force, the hydrostatic balance, the horizontal pressure gradient force with the geostrophic flow and the horizontal balancing the pressure gradient and the horizontal. This has all three of those numbers small, which is means that friction is negligible, so we're outside the Ekman layer, and advective and temporal Rossby numbers are small, which means that we're thinking about relatively weak currents and relatively slowly varying currents on the time scale of a day. This is large scale phenomena that are going to have the Rossby number small enough that we can get a geostrophic balance. The Taylor-Proudman theorem, we have now learned, is not independent of the geostrophic balance. Instead, look, geostrophic balance has those two terms, kind of half of that term, this part of the pressure gradient force and the Coriolis force are involved in the Taylor-Proudman, but so is gravity. So let's go back. Hydrostatic balance, geostrophic balance, Taylor-Proudman. Wow, they're starting to highlight these same three terms. The only one that's not highlighted is this pressure gradient and gradient of density one. We saw that if it's barotropic, then it actually still holds, but if it is not barotropic, then this term could be interestingly different from the Taylor-Proudman theorem, and we can get vertical shear and a geostrophic flow. We're going to come back to that in just a second. Okay. Now, we've got these different limits on the equations of motion. We've got them in the inertial oscillation range. We've got them in the Ekman flavor. We've got them in the geostrophic flavor. How do we think about putting all those pieces together? We talked in the tank like there was an inertial oscillation superimposed on a geostrophic flow. And then I said, hey, if we'd gone down into the bottom Ekman layer, we would have seen an Ekman flow just kind of superimposed, like we keep talking about. There's a shear within that frictional layer, and then the geostrophic flow goes together, but up here in this layer, it's just the sum of the Ekman flow and the geostrophic flow. How does that work in the equations? Well, what if we have a total velocity that's just the sum of the solution to the inertial oscillation equation plus the solution to the Ekman equation plus the solution to the geostrophic equation? Well, the Coriolis force in each of those, F cross V inertial, plus F cross V Ekman, plus F cross VG, because that's a term that's linear in velocity, it just distributes over all three. So I have F cross the sum of VI plus VE plus VG. So this term, F cross VI plus VE plus VG, just becomes the sum of the three terms. And now I know that F cross VI balances with d by dt of VI. So the time-dependent term is going to be balanced against the Coriolis force on the inertial oscillation. Now what about the Ekman component of the time dependence of Ekman? Well, we've by assumption assumed that the temporal Rossby number of the Ekman flow is small, which means that the Ekman flow changes slowly in time, which means that there is no ddt of V Ekman to worry about balancing. That's a small term. Same thing with the geostrophic force. The ddt of Vg we assumed had to be small, so there's nothing to balance. So the ddt term is balanced against only the inertial part of the F cross Vi. So we've taken care of this balance with 1/3 of this term. We go through exactly the same logic. We take the F cross Vg term, and that balances this. And this balances this, because if we're in the hydrostatic geostrophic balance, we've actually got the vertical momentum equation. So now we have this term, this term, this term taken care of and balanced when we have F cross VI plus F cross VG in this term. And the only one that's left is the friction, and that's only in this surface layer, and we take care of that one by just having the F cross VE added. So F cross VE here has negligible pressure gradient, negligible effect on gravity, negligible effect on time, but has a non-negligible effect on the friction, and that's the part that balances. So if we sum this up, bing, 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 in this equation, we actually solve the whole thing by summing up those different components separately, with each of them obeying the advective Rossby number, temporal Rossby number, Ekman number that we had assumed from before. Why doesn't this actually work in the real world? And this is the distinction between the model we are assessing, which solves the full equation with all the terms in the equation, and these theoretical limits under particular assumptions of the equations of motion. Notice that there's a term missing from this equation. It's the v dot grad v term. V dot grad v term, when we put that one back in, we have a problem, because the vi dot grad vi plus the ve dot grad ve plus the vg dot grad ve term surely does not add up to the sum of those three terms. We're missing all of these cross terms in red below. This nonlinear term invalidates the principle of superposition. Superposition is what I was just describing, where we just add the different velocity fields to each other. That only works in a linear differential equation. It does not work in a nonlinear differential equation. So how do we get around it? Well, we got around it because for all three of those phenomena, inertial oscillations, Ekman transport, and geostrophic transport, the advective Rossby number was small. So none of them were big enough to have a big nonlinear term. If that is true, then we are in a relatively linear set of equations, at least from the perspective of the momentum equation, and we can just add together the different components of the velocity and get the total. If it's not true, if we have, what's the advective Rossby number? Remember, it's v over f times L, and the velocity scale over f times L. So if it's a really fast current or it's a really narrow current, we get in big trouble. We can't neglect this term, and that's what we're stuck with. The full nonlinear system. So the model is solving the Echo model is solving the full nonlinear system. So in a sense, when we're diagnosing these different components of the flow one at a time, what we're doing is we're just checking how important the terms we're neglecting are. That's the essence of non-dimensionalization and scaling of sets of equations. Okay. But I will tell you that at the resolution that the Echo model is at, almost everywhere in the world, this linearization works pretty well. So we're off and running. We can just separately diagnose these pieces, add them back up, and we get really close to the full answer. So that's the game we're playing. We've been diagnosing the Ekman for this. We diagnosed the Ekman for the paper you guys are working on. We're going to diagnose the geostrophic velocity for the paper that's after. If you really wanted to get ambitious and also diagnose the inertial contribution, you would have essentially the whole of what's going on in this model. And that's what's going on in the rotating tank. I'm not going to play that video again. This rotating tank experiment that we've been talking about is actually coming from the John Marshall's GFD lab, and it has a nice description. There are lots of other GFD experiments. You can also see Ekman and inertial oscillations, and it's a similar setup. It's worth going and browsing on their website for the GFD lab. Here's a nice example of a geostrophic flow that they have set up, where they have a drain hole in the middle. And if their rotation weight is weak, they're just dropping a buoyant particle on the surface of the ocean. It pretty much goes down the plug hole. It doesn't go quite in, because there is some rotation in this tank, just not fast rotation. So this is in the limit where there is a Rossby number, where the Rossby number is not small. The Rossby number is kind of order 1. It's mainly going down the plug hole. Here's a case where the rotation rate is much faster. And you notice that the parcels and the fluid velocity, rather than going directly down the plug hole, goes around and around and around and around. This is a low pressure anomaly because the plug hole is sucking stuff out the bottom. It's going cyclonically, so that is in the direction of rotation of the tank. And it doesn't go straight down, it goes around and around. So these lines in the steady state balance of this are actually indicating they're parallel to the sea surface height anomaly as we go from the low near the plug hole to the high out here where the source is. All this funny stuff out here are rocks to make the inflow uniform through the coming to replace the water that's going out the plug hole in through the sides, but without any initial velocity. And it goes, so the flow goes more or less along the ISO sea surface height surfaces. The ISO bars is also in the same direction because this is a constant density fluid. So the sea surface height is the only way that the pressure field varies in the horizontal. It varies because the sea surface height varies. Yeah, and this is a barotropic flow as well. This is a trivial barotropic flow. Okay, so there's a great Simpsons video. This is all inspired by toilets flushing. So Bart is trying to get his toilet to flush in the anticyclonic direction, and he's burning up the family. I won't play this whole video. You can go search for this online. It's very funny. He calls up the Southern Hemisphere to see how their toilets work. It's a whole mess. All right. There are entire web pages debunking misapplication of this plug hole in a rotating tank problem, plug hole in a rotating earth problem. Here are two nice, interesting examples. There are people who do all kinds of stuff with this. It's fun to think about. I encourage you to search around on the web. Okay, what happens if we are not barotropic? That's the last thing I want to talk about before we close this video. So here's what barotropic looks like in terms of pillows and bricks. So the sea surface height, high pressure, low pressure, because this stack of pillows starts higher up than this does. So here is an ISO bar looking from side view. At the bottom of the stack of pillows, this stack of pillows is just as tall as this stack, so there's the same isobaric slope here. And then we put the same height stack of bricks, and we get the same isobaric slope down here. So the pressure surfaces are still only functions in the horizontal of the sea surface height, even though the density is varying in the vertical. It's varying in the vertical in a way that it is only a function of the pressure. So high pressure, low pressure, we would expect there to be a geostrophic velocity coming out of the page in this case in a northern hemisphere kind of configuration at all depths of the same, because this pressure gradient in the horizontal is the same. It's the constant in the vertical. What if we have a stack of pillows next to a stack of bricks? Now we're playing a different game. The density is now not a function of pressure, it's a function of location. Here's high density stuff next to low density stuff at the same pressure level. So how does that play out? Well, the weight above you is accumulating fast here. The weight above you is accumulating slow here. So we expect the pressure increase here to be slower on this side than it is on this side. So if we start with a high pressure on this side, because this stack of pillows is slightly higher than this stack of bricks, we have a lower pressure here, so we might have a pressure gradient force pointing this way at the surface. But now as we go down in this cold, dense column, we're accumulating pressure faster. So now the high pressure at this depth is on this side, lower pressure on this side. So the pressure gradient force is pointing the opposite way. So in this situation where the density varies in the horizontal, we see that we are not just we're getting reversals in the direction of the pressure gradient force with depth. And if the pressure gradient force is linked, as we've just talked about, to the Coriolis force, and the Coriolis force is linked to the geostrophic velocity, that means that the geostrophic velocity is flipping sign in the vertical. It's going from out of the page at the top to into the page at the bottom. This vertical variation in the geostrophic velocity is called the thermal wind equation, or the thermal wind relationship. This location of low density next to high density at the same pressure level is called baroclinicity. This flow is baroclinic. Baroclinic is the exception to the rule of barotropic. It means that the density is varying for reasons other than due to pressure. So here the density is varying because in space, in addition to varying in pressure. What's the math behind the thermal wind equation? Well, we've still got, it's still a geostrophic flow that we're contemplating. Here it is. But now we have a more complicated pressure gradient force because the density is varying not only in pressure, but also in X and Y. So, what can we do? Well, we can actually not take the pressure itself. We can't eliminate the pressure with this equation because this is ddz of the pressure. But what if we take ddz of this whole equation? F doesn't change in the vertical. So this ddz of this side is just F cross ddz of V, which equals ddz of the pressure gradient force with the density downstairs, which is approximately equal to, for reasons of the Boussinesq approximation, we can replace this density down here with the background density value, bring this ddz inside, this ddz going inside gives us dpdz upstairs, dpdz upstairs, which then is the same as rho g. So this is minus the gradient of the buoyancy. So F dv dz equals the horizontal equals the gradient of buoyancy, which is the same. And here I'm introducing the buoyancy, which is a way of rewriting the density in a simple way, but here it is. It's just the density anomaly from the background density divided by the background density and in units of g. Why this is convenient is just because it makes this equation simple. Instead of writing the horizontal gradient of density with a minus sign, we're writing this other thing, this buoyancy, and it sucks up that rho naught on the bottom and it sucks up that g in the top, and it makes it nice and clean. This guy plugged into there gives us backwards this whole equation. So if there are horizontal variations in the buoyancy, that is if the density deviates from its background value, then you will have vertical shear in the geostrophic velocity, which means it's no longer subject to the Taylor-Proudman theorem. What? This is exactly what was prohibited by the Taylor-Proudman theorem, is horizontal variations in the density, horizontal variations in the buoyancy. That was not allowed. Now we've got them. When we've got them, we now get vertical shear. So we don't have Taylor columns in the presence of horizontal gradient variations in the buoyancy or density. You can also write it this way. If you want to play that same game with the back cab rule, you can write it as the shear in the geostrophic velocity goes with the horizontal gradient in buoyancy. Or you can write it this way, that the Coriolis force, the ddz of the Coriolis force is balanced by the buoyancy gradient. And so you think of these complicated kinds of schematics where the isobars are tilting and so are the isopycnals, that is the density, constant density surfaces. This one is a barotropic flow, which doesn't give you a vertical shear. This one is a baroclinic flow where the isobars are going one way and the isopycnals are going the other way. And in this case, you have vertical shear with the arrows getting weaker as you go with depth. And in this case, you don't have vertical shear because it's barotropic. So you get the same velocity value all the way down. Okay. What about the real world? Let's jump back to this model where we showed the pressure surfaces near the surface. They are the highs in these anticyclonic. Now we know they're anticyclonic gyre circulations in the subtropics, lows in the subpolar regions and around the ACC. We can now say that the geostrophic velocity is traveling along these pressure lines. And because these are the isobars, so it's perpendicular to the pressure gradient. The pressure gradient points from one isopycnal isobar to the next. So the geostrophic flow is going around and around on these isobar surfaces. Cool. The ACC is going this way. And we know that it's cyclonic where it's a low in the middle. It's anticyclonic where there's a high in the middle. So an anticyclone here is clockwise in the northern hemisphere, counterclockwise in the southern hemisphere. What if we go deeper? Is there a barotropic or a baroclinic response? Well, the ACC is weakened somewhat, so it has some baroclinicity, but there's enormous baroclinicity going on underneath the gyres. The gyres have basically vanished. That's because the peak decline is depressed everywhere where there is a sea surface height anomaly, which means that the baroclinicity is essentially canceling out the barotropic component of the velocity in such a way that when we get to deep flow, there's relatively little motion. So we have lower velocities, lower geostrophic velocities when we get down to 1,500 meters depth than we did at the surface, and that's because of the combination of the sea surface height anomalies that are basically driving these high and low pressure zones together with the deviations of the baroclinic part that is the picnic line.